Everyone, and welcome to lesson 6 on parallel plate capacitors. So parallel plate capacitors are really important. We're going to be using them a lot in this course, and we've actually already started looking at them, which we'll see here in just a moment. But the objective for this lesson is to be able to describe and quantify the motion of charged particles and of dipoles in uniform electric fields. So in the previous lesson, we said that an electrode was a flat charged surface. And it's essentially any plane, infinite plane with, you can model as an infinite plane, and it could have any shape. It doesn't have to be a disk, it doesn't have to be a square, it could be anything. Okay, so when two electrodes are close together and oppositely charged, we refer to this as a parallel plate capacitor. Okay, and so if we deposit some charge on one plate, so I have this is a parallel plate capacitor that we have here, and it's essentially two disks. And they're separated, and you can adjust the distance they're separated by. You can push this thing, and it'll go back and forth. Okay, and we can see there's some insulation here so that the charge doesn't escape. And so essentially, we could deposit some charge on one plate. Maybe we could rub a rod with some fur and touch it to this plate. Okay, and so what we would see here then is we would get some negative charge collect on this plate, and then so this side is insulated, so the charge will stay on there for a time. But even though this side is not really insulated, what we see happen is that polarization occurs, right? So we saw polarization in an earlier lesson, and so if we added some negative charges on this side, it would cause this polarization to occur. And then so the other side would have a positive, would be positively charged. Okay. And so what this does is all of the charges we see, the positive charges on the one plate will collect on the inside, right? So I'm referring to this as the inside of the capacitor, and all the negative charges move to this side. Okay, so we get this polarization happening, and so the net field inside the capacitor, okay, is going to be it's going to point from the positive plate to the negative plate. So we're going to get electric fields that, hopefully you can see this green. Okay, pointing from the positive plate to the negative plate. Okay, and so this essentially what happens is we get a field inside, okay, but nothing outside, okay. So that's what we want to worry about is right in there. Okay, so we learned that the electric field of one electrode is eta over 2 epsilon naught. They have one infinite plate of charge. Okay, and eta was charge per area. Okay, so we could say charge per area 2 epsilon naught. Okay, but we have two electrodes here, right? We have two parallel plates. Okay, and so if we have two, right, then this is basically 2 times E. Okay, which is 2 Q A 2 epsilon naught, right? Then we see that the 2's cancel out, right? And so the electric field inside the parallel plate capacitor is just Q over the area times epsilon naught. Okay? And we saw this. We already did this in the previous lesson when we did the example problem of the two disks of charge separated by a small distance. And we found the electric field at the midpoint. And we saw, well, what force would a 1 nanocoulomb charge experience if we placed it there? Okay, that was actually a parallel plate capacitor. Okay, because there were two plates oppositely charged, parallel to one another. Okay, and so we saw that, right? We found the Q over, right, or the eta over 2 epsilon, or the Q over charge per area 2 epsilon, and then we saw we had to add it, right? We found it from one plate, and then we basically doubled it. Okay, well, this is just a way that we can double it, right? Because basically, originally we had, if you could pull this 2 in the denominator out and make it a half, right? And then if we double it, that half just turns to 1. Okay. So that's the electric field inside a parallel plate capacitor. Now, a parallel plate capacitor, like we see here, they're parallel, and so the lines, the field lines, point from the positive plate to the negative plate, and those lines are parallel to each other, right? So what this effect does is it creates a uniform electric field between the plates. Okay, so that means the strength of the electric field everywhere, anywhere you pick, is going to be the same. The direction, anywhere you pick, is always going to be the same. Okay, so a parallel plate capacitor is probably one of the easiest ways to create a uniform electric field. And so if you ever encounter a problem that refers to a uniform electric field, you could probably assume that the scenario is talking about a parallel plate capacitor. Okay, so let's try an example of this. So air breaks down when the electric field strength reaches 3 times 10 to the 6 newtons per coulomb, and this causes a spark. So you've seen this, and if you want to create a spark between a parallel plate capacitor that is made from 2 4-centimeter square electrodes, how many electrons must be transferred between the electrodes? Okay, so well, an electron is just a charge, so we essentially want to know how much charge there is. Okay, well, that relationship is the electric field inside a parallel plate capacitor is charge over epsilon naught times the area. So if we solve for Q, right, we get electric field times epsilon naught times the area. Okay, so the electric field we're given is 3 times 10 to the 6 newtons per coulomb. Epsilon naught is 8.85 times 10 to the minus 12th. And then the area, okay, so if we have a parallel plate made up of 2 4-centimeter square electrodes. So these are square electrodes, 4 centimeters on each side. So the area would just be, if we put it in meters, 0.04 meters. Square that, and that gives us 0.0016 meters squared. Okay, so then that total charge, when we do that all out, I get about 42 nanocoulombs. Okay, so that's the total charge that's required to create this spark, and so we want to know how many electrons. Well, 1 electron, and you can look this up, it's in your book, and probably Google it. The charge of 1 electron is 1.6 times 10 to the minus 19th coulombs. Okay, but we have 42 times 10 to the minus 9th coulombs. So how many electrons is this? Well, this is just simple division now. 42 10 to the minus 9th coulombs per 1.6 times 10 to the minus 19th coulombs. per electron. Okay, and I get about 2.7 times 10 to the 11th electrons. Okay, quite a bit. So I actually have a little old machine we have here that will actually kind of create a spark. It's sort of like a parallel plate capacitor, but um, it's more almost like, instead of plates, are almost like spheres. So I'm gonna show you that quick here. Okay, so I have this kind of ancient machine, like I told you, and essentially what it is um, it's pretty complex, but it essentially, there's some static electricity. There's some brushes, and there's two wheels here that spin, and brushes touch each other, and that kind of rips electrons off. And then these are called Leyden jar capacitors, and then they go up and they touch to these two balls here, and they're separated by a couple inches. And once we get enough electrons between these two capacitors, then we'll see that spark. Okay, so now with so that's one thing we can do with a parallel plate capacitor. Um, now since a parallel plate capacitor uh, creates a uniform electric field, and we could also recall that a charge Q that's in the presence of an electric field will experience a force, according to this, right? We've done this a few times. And so if this is the only force that's acting on the charge, then the force causes the particle to accelerate. Okay, we've seen this before. And so the acceleration, right, from F equals ma, right, we get ma equals QE. And so the acceleration will be charge times electric field over mass. Okay? So we can figure out how much it accelerates. Now, here's the fun part, is that if the electric field is uniform, like it is in a parallel plate capacitor, guess what that means for the acceleration? It's a uniform or constant acceleration. We get to apply our constant acceleration model we learned from 151. All right, I know you were looking forward to that. Okay, I'm just sitting here by myself, make myself laugh. That's all, you can laugh at me. All right, so let's look at a parallel plate capacitor that has 2 centimeter square electrodes. Okay, so I drew them here. So these are 2 centimeter square. So we're sort of looking at the side of it, the side view. So we got the negative plate here, the positive plate here. And they have surface charge densities of plus or minus 1 times 10 to the minus 6 coulombs per meter squared. So why plus minus? Well, because one is charged positively, one is charged negatively. Okay, but they each have the same amount of charge. Okay, the positive plate has 1.6 or 1 times 10 to the minus 6 coulombs per square meter, and the negative charge has negative 1 times 10 to the minus 6 coulombs per square meter. Okay, and then we have a proton traveling parallel to the electrodes at 1 times 10 to the 6 meters per second. Okay, so it's traveling parallel. That means it's going like this. Okay, it's entering the parallel plate capacitor like this, and it enters the center of the gap between them. Okay, so before we go to the question, I'm going to actually create an XY axis here. Okay, it's going to help us out. Create the XY axis right there at where the proton is entering. because we're told that it's entering right there at the center between the electrodes. Okay, so that's X, that's Y. Okay, so the proton traveling parallel to the electrodes, right? So it's going in this way. The electrodes it's going parallel to the electrodes. And then it enters the center of the gap between them, okay? And so what's going to happen? What does the electric field look like inside the parallel plate capacitor? Right? The field lines point from the positive plate to the negative plate. So we're going to have field lines like this. Okay? All the way throughout. Nice, straight field lines. I don't know if I'm drawing them perfectly straight, but I'm trying. Okay. So that's what the field looks like. It's a uniform field. Now, if a proton or any positively charged charge enters this field, what's it gonna do? Okay, positive charge, it's gonna enter the field. It's gonna want to do what? It's gonna want to repel the positive plate and attract to the negative plate. So, the path, what path is it gonna follow? It's gonna, as soon as it comes in here, it's gonna get deflected. Okay, like that. Sort of looks like projectile motion, right? Kind of looks upside down because we're used to looking at projectile motion as falling down to the earth, but this is projectile motion essentially. And so the question now is, by what distance has the proton been deflected sideways when it reaches the far edge of the capacitor? Okay, so maybe my more accurate depiction of this is that it's going to go all the way to the far side like that, follow some sort of projectile path. Okay, reaches the far edge. So how far is it going to go? I mean, I don't know if it'll hit the plate, or maybe it'll just go this far. We don't know. But essentially, what we want to do is we want to know what's the distance it's going to move. Okay, and so this is where our coordinate system is going to help us. Okay, so the proton is said to enter the center of the gap. Okay, so that's perfectly on the x-axis. Okay, but what's going to happen to it? It's going to move in this projectile motion type of way, and so it's going to move in the x and y plane. But all we care about is what? By what distance has it been deflected sideways? Okay, so that essentially means the distance. Right, what distance here? Right, this we could call delta y. Okay, so sideways is essentially along the y-axis. Okay, so this is where we get to use the fact that we want to find the distance. Well, we know that it's a uniform electric field, which means it undergoes a constant acceleration. Okay, so if we can find that acceleration, then we can apply the constant acceleration model to figure out that distance. Okay, so how do we find acceleration? Right, we said it was the charge times the electric field divided by the mass. Okay, so what's the electric field here? We need to know that. So the electric field is charge over epsilon naught A. Well, the charge per area, we've already been given that, right? The surface charge density. Okay, so we could, if we wanted to, we could rewrite this as eta over epsilon naught, because that's what we were given. We were given was eta. which is 1 times 10 to the minus 6. Okay. And then epsilon naught, 8.85 times 10 to the minus 12 will give us an electric field of 1.13 times 10 to the 5th newtons per coulomb. Okay, now we should be able to find the acceleration. All right, so it's a proton. All protons have the same charge and same mass. The charge of a proton is actually the same as the charge of an electron. So it's 1.6 times 10 to the minus 19th coulombs again. Then the electric field we found, 1.13 times 10 to the 5th newtons per coulomb, divided by the mass. And so the mass of a proton, 1.67 times 10 to the minus 27th kilograms. So although electrons and protons have the same charge, amount of charge, they don't have the same mass. So that's the only difference. Okay, so if we plug this in, we'll find an acceleration of 1.08 times 10 to the 13th meters per second squared. Okay, so now we know how much the electric field, is going to cause the proton to accelerate. Okay, so this is constant acceleration. So we can apply the constant acceleration model. So we're looking for delta y. So we can look at our constant acceleration model, those equations that we developed in 151, and we can figure out, all right, where's delta y? How can we figure that out? So delta y is the initial velocity in the y times the time interval plus 1/2 acceleration in the y times the time interval squared. Okay, and change some colors here for a moment. And what do we know about the initial velocity in the y direction, the y component of the initial velocity? Well, remember, like with projectile motion, what's going on here? The proton is traveling parallel initially to the plates, so it means it's traveling perfectly before it enters the parallel plate capacitor. It's traveling perfectly along the x-axis. So that means, what do we know about its initial y component of its velocity? 0, right? So we've done this before when we shot a projectile horizontally. So then we could say this whole term goes to 0. So then that deflection, that displacement, is just 1/2 the acceleration, which we calculated, times the time interval squared. Ooh, we don't know the time interval. But recall, from projectile motion and constant acceleration model in general, what do we know about the time? Okay, so we want to know the time it takes. So it's the time it's over while it's being deflected along the y-axis, but that's the same, right, as the time it moves horizontally, the time it takes to move horizontally, right? Those are the same. The time is one thing that stays the same for everything. Okay, so if we could find the time interval it takes the proton to move horizontally, we can use that because it's going to be the same to move vertically. So how can we find time interval? Well, we can likewise basically use the same constant acceleration equation, and this time for the x along the x-axis. So its displacement is its initial x velocity times the time interval plus 1/2 acceleration in the x direction times the time interval squared. Okay. So now that might look like we need to use the quadratic equation, but what do we know about the acceleration in the x direction? Okay, what are we told? The proton travels parallel at 1.6 or 1 times 10 to the 6 meters per second. It's not accelerating in the x direction. It's moving at this velocity of 1 times 10 to the 6 meters per second. The only acceleration is perpendicular, right? Is in the y direction. Okay, so this acceleration is 0. Okay, so then this whole term goes to 0. So then what we're left with is delta x is Vix delta t. And then we're looking for delta t. Delta t is delta x over the initial velocity in the x direction. So what's its x displacement? Well, it moves through the parallel plate capacitors. They have the area is 2 centimeters by 2 centimeters, right? Yeah, 2 centimeters squared. So the x distance it travels is 2 centimeters, right? Because that's what we're looking for, is by what distance has the proton been deflected when it reaches the far side of the capacitor. Okay, so that's our delta x, 2 centimeters, or 0.02 meters. Keep our units consistent. And its initial velocity in the x direction, we were told, was that 1 times 10 to the 6 meters per second. Okay, so now this gives us a time interval of 2 times 10 to the minus 8 seconds. Okay, so this happens very fast. Okay, and so since it took 2 seconds, 2 times 10 to the minus 8 seconds to move horizontally, that's the time it's moving vertically as well. Okay, so then that vertical or sideways displacement deflection is 2.16 times 10 to the minus 3rd meters. That was fun. So like a little intellectual workout, like a little puzzle we just solved. Okay. All right, so let's think about this conceptually here. Let's say we have a proton moving to the right, like shown here with the green arrow, in a vertical electric field. Okay, so it's moving perpendicular to it. So a very short time later, what is the direction of the proton's velocity? Okay, so which way is it going to move? Well, the field is vertical, but we can see by the arrows in the field that it's pointing up, right? And when it's pointing up, what does that mean? Right? It means lines that they have to come from some sort of pointing away from positive charge and toward negative charges. Okay, so this looks like it could be a parallel plate capacitor. Okay, so if it goes through here, what's it going to do? It's going to repel the positives and attract to the negatives. So it's going to do something like this. That might be the direction of the vector. You know, it'll actually follow a parabolic path now, though. Okay, so since we get a uniform electric field from a parallel plate capacitor, we can use them to accelerate charged particles, which is something we like to do in physics. And so here we have, it's a Crookes tube or a cathode ray tube. And what we do with this is we set up a parallel plate capacitor inside of it. So this tube is vacuum sealed, and there's a parallel plate capacitor inside of here, okay? And so we use this we can see I have some things plugged into the different sides of the capacitor and a big power supply. And essentially, since there's a uniform electric field in here, okay, and then we have this plugged in, we get some electrons from the source of electricity. And once they come in here, they get accelerated, boom, Okay, and there's this gas inside the tube that when the protons move, they light up green. And so we'd actually see them. And this is exactly how the original televisions, even up to the ones we've had maybe 10 or so years ago with the big box ones. This is how they worked. Okay, same with older computer monitors. Okay, so I want to look at last thing here is I want to look at dipoles briefly. We're not going to do a whole lot of we're not going to do any real calculations with them, but I want you to understand conceptually what happens when they're in a presence of an electric field. Okay, so when we do place an electric dipole in a uniform field, right? So this is our dipole here. All right, a dipole is just when we have a positive and a negative charge kind of hanging out together. They're one team, and so what happens if you place it in a uniform electric field is that it experiences a net force of zero, right? Because all right, so we see our electric field here is pointing from left to right. It's a uniform field, and so what do we know is going to happen? Is that it's going to line up, okay? It's going to, the electric field is going to exert a torque on the dipole and cause it to rotate, okay? And so we say there's a net force of zero because it experiences a force this way and a force this way, and they're completely equal, okay? And so what the torque does is that it causes the dipole to rotate until it's aligned with the electric field. Okay, so we point, right? We point from positive, so there must be some positive charges over here, or maybe this is a parallel plate capacitor, and there should be some negative charges here. And so, of course, the positive's going to want to be attracted toward the negative, and the negative's want to be attracted toward the positive, and so it's going to rotate. It gives it a torque, okay? But it's equal. The forces are equal, so really it's a zero net force, okay? And then they're going to rotate. It's going to rotate until it lines up with the field. So like we have down here. Okay, and so when permanent dipoles, like water molecules are permanent dipoles, when we place them in an electric field, all of the dipoles rotate until they're aligned with the electric field. Okay, and so the result is that the water molecules, the sample of water molecules becomes polarized, so that the excess negative charges flow to one surface. Okay, negative, 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 or the other way around. Right? No, negative. Yeah, that's right. All right, negative, and then positive to one surface. So we get this polarization occurring, okay? And so one attribute of an electric dipole is that it has what we call a dipole moment, okay? So remember with torque, we had that moment arm or that lever arm. And so the dipole moment describes the dipole's charges and the separation of the charges. So we're not going to do anything with this, but just kind of it's going to help. But we're not going to do any calculations with this, but it's going to help us to understand more conceptually what's going to happen. So the dipole moment we symbolize with lowercase p, and it's the charge times this distance s, which is just how much they're separated by. And so the direction of the dipole moments will tell us how the dipole is oriented, and the magnitude will help us quantify the electric field that the dipole itself is creating. Okay? And so the torque that the dipole experiences in the uniform field. And remember torque, we did that tau is the dipole moment, the cross product of the dipole moment, and the electric field. So these are all vector quantities. Okay, and so that's that was a uniform electric field. Now I just want to briefly look at what happens in a non-uniform electric field. When you place a dipole in a non-uniform electric field. So remember that a point charge, uh, um, it does not create a uniform electric field, right? It's got a stronger electric field closer to it and a weaker field away from it. And so if we place a dipole somewhere near the point charge, it's now in this non-uniform electric field. And so if we're looking at this example here of a positive point charge, then the dipole is going to rotate until it lines up with the electric field, right? So with the positive side over here, because it wants to repel the positive point charge, and the negative side facing the positive point charge because it wants to attract toward it. And so now what we see is that the negative side of the dipole is now closer to the positive point charge. Okay, the result is that the attractive force between the negative side of the dipole and the positive point charge, that attractive force is now stronger than the repulsive force between the positive end of the dipole and the positive point charge, right? Because this side is closer. Okay, and so the dipole then experiences a net force toward the point charge. Okay, so for any non-uniform fields, the net force on a dipole, okay, is always in the direction of the strongest field. Okay, so the electric field of a point charge or any charge object, remember, gets stronger the closer it gets to anything. So we get this net force toward it, which means it's going to accelerate toward it. Okay, so now you should be able to finish up the problems for homework 2. Okay, so this will finish up all the chapter 23 stuff and everything you need for homework 2, and a couple more example problems if you need more practice. And so did you learn to describe and quantify the motion of charged particles and dipoles in uniform electric fields? So we learned about this important thing called a parallel plate capacitor, which creates a uniform electric field. The field lines point from the positive plate toward the negative plate. Okay, we learned how to find the electric field strength inside a parallel plate capacitor. Okay, and remember that the field strength is the same. It's a uniform field, so it's the same magnitude everywhere, and it always points in the same direction. And if we put a charge in there, well, the charge will experience a force, and since it's a uniform field, constant field, we can apply the constant acceleration model to it. Okay, so we can find out all kinds of things about how it moves around in there and apply the constant acceleration model to it. And we saw then finally that how dipoles will kind of line up with the field. And so if it's in a uniform field, it just kind of lines up with the field, can create some polarization. And if it's in a non-uniform field, right, it will also experience a force and an acceleration. Okay, so that's it for lesson 6.